Alright guys, we're going to go ahead and get started with these Webwork UCM Orbit problems. And our first problem says the planet blank, or question mark, has a mass of 8.68 times 10 to the 25th kilograms. So I'm just going to go ahead and write M1 here because I know that this is going to be my first mass. And a diameter of 51,118 kilometers. Okay, so some important things. We have kilometers here and we have diameter, so we want to make sure we're paying attention. And it says the center of our planet is located 2.87103 times 10 to the 9th, again kilometers, away from the center of the Earth. All right, so center to center, this is good information. And the sun has a mass of 1.989 times 10 to the 30th kilograms. So this is most likely my M2, but let's read the question to figure out exactly what it's asking us for. So number one says, what number should be R in the equation below? Well, below it's asking us to solve for the centripetal force that keeps our planet orbiting around the sun. So really quickly, let's just draw a picture of that. So here is the sun, okay? And then here is our planet that is orbiting around it. And we know that the orbit is going to look something like this because it's experiencing uniform circular motion. So if this is our planet and this is our sun, we need to find the distance between those two centers. So from here to here. And this distance r, right, is going to correlate to this number right here. 2.87103 times 10 to the 9th kilometers, because this is the center of our planet to the center of the sun. Something to note though is that it's in kilometers, and in order for us to use it for R, we need to convert it to meters. So we need to multiply by 1,000 or tack on another 3 to the exponent. So this turns into 2.87103 e to the 12th meters. Next, it says calculate the centripetal force that keeps our planet orbiting around the sun. Well, the centripetal force is going to be the force that points towards the middle of its orbit. So what force is pulling this planet towards the other planet? Well, that's going to be forced gravity. And fortunately for us, we have an equation for forced gravity, and that's just up here. And it tells us forced gravity is equal to big G times M1 times M2 all over R squared. Since the orbit is around the sun, we're going to take this mass over here, which is the mass of the sun, and set that for our M2. And our planet is going to have the mass right here as M1. Both of these masses are in the correct unit, so we can just go ahead and plug them in. So I'm going to write that down here just so that we can see. So if I'm solving for forced gravity, I get forced gravity equals big G, and we know big G is just 6.67 times 10 to the negative 11th times M1, which is 8.68 e to the 25th times M2, which is 1.989 times 10 to the 30th, all divided by R squared, and our R value was 2.87103 e to the 12th. And we can't forget it's squared. Next, we'll just go ahead and plug all this information into our calculator, and we find out that forced gravity for our planet, or the centripetal force that it is feeling, that is stopping it from flying off in a straight line. Because if we were to make the sun disappear right here, there would be no forced gravity. And if there was no forced gravity, this planet would just fly off into the abyss. But since we have forced gravity, we are not going to fly off into the abyss. We're going to stay in orbit around the sun. And this forced gravity should be 1.40 e to the 21st newtons. And you're going to notice that this number is pretty big. And that makes sense, right? Because we're talking about the sun here and our planet. And they're going to feel a huge amount of attraction. And that's why our planet is orbiting around the sun, because it has such a huge pull on our planet. Now that we have number 1 and 2 done, let's take a look at number 3. Well, number 3 says, what is the centripetal force that keeps our planet from flying off? We just talked about this. that centripetal force is the force that points towards the center. That's going to be force gravity. And we already solved for it below. Next, it's going to ask us to calculate the centripetal acceleration of our planet. Well, centripetal acceleration, we need to look at our equations. We see that we have one right here that tells us what centripetal acceleration is. Unfortunately, this equation requires us to know what velocity is. We do not know velocity at this second, so we cannot use this equation. Fortunately for us, we have Newton's second law, and Newton's second law has acceleration in it. But it talked about centripetal acceleration. So in order to find that, we just need to take net force centripetal, and then we have centripetal acceleration. So we just add two little tiny c subscripts there in order to allow us to use this equation. And I go ahead and write net force equals ma subscript c, right? Because this is about centripetal force. Well, what were the forces that pointed towards the middle of our orbit? There was only one force, and we said that was force gravity. So our net force centripetal is just force gravity. And then the mass here, well, this is the mass that is experiencing this net force of gravity. It is also the mass that is experiencing the centripetal acceleration. So if we look here, which mass is the one that's orbiting? Is it the sun or is it the planet? Well, it's the planet, because the planet's smaller than the sun and the planet is what orbits around the sun. So this mass is going to be the mass of our planet, so I'll just write MP, times that centripetal acceleration. So if we want to solve for centripetal acceleration, let's divide the mass over to the other side. We get force gravity divided by the mass of our planet is equal to centripetal acceleration. We plug in our numbers. Our force gravity is right here. The mass of our planet we have from above, it's 8.68 e to the 25th, and we just plug in accordingly. We find out that our centripetal acceleration for this planet is 1.61 e to the negative fifth meters per second squared. Now that we've calculated our centripetal acceleration, we want to find out what direction does it point. Well, this is the same that it's always been. Acceleration in terms of net force is going to point in the same direction as that net force. And since our net force is only force gravity, and since force gravity is pointing towards the center of the planet, our acceleration is going to point towards the center of the planet. All right, now that we've talked about what direction it points in, let's move on to velocity and let's calculate that. So if we look up here at our equations, we have two equations again that have velocity. All right, so if we look at this equation, our distance equals rate times time for velocity has time. Unfortunately, we don't know time, so we can't use that one. So we're going to have to use this equation over here, our centripetal acceleration one. And this one has centripetal acceleration, which we know, velocity, which we're trying to figure out, and r, that we also know. We just need to make sure that we're plugging in the correct r here. So let's scroll down and let's go ahead and write that equation. AC is equal to v squared over r. Well, it's asking us to calculate the velocity. So let's just manipulate this really quick to solve for velocity. Go ahead and multiply this r over here. We end up with r times centripetal acceleration is equal to v squared, square root both sides, and we find out that v is equal to the square root of r times centripetal acceleration. So we mentioned before, we know what centripetal acceleration is. We just solve for it. That's right here. But we need to think about this r value. Well, this r value is going to be the same r value as the one in our force gravity equation. And the reason why it's the same r as the force gravity equation is because this r represents, again, the distance from the center of one object to the center of the other. And it's our centripetal acceleration about that orbit. So the orbit, right, relies on this distance r from the center of one to the center of the other. So once we go ahead and plug in all of our numbers, we find out that our velocity should be 6,797.69 meters per second. Next question asks, what direction is the velocity point? Well, we've talked about this a few times, and the velocity is actually going to point tangent to our orbit. or perpendicular to the net force and centripetal acceleration. So let's talk really quickly like what that means. And if this is our orbit here, our velocity is going to point in this direction. And that's just telling us that if the sun were to disappear, right, we were to get rid of it, that our planet would fly tangent from that orbit forever. So it would just fly in this direction like we just pointed forever. And that's because no other objects would have a gravitational pull on it, assuming everything else in the universe disappeared, right? It would just continue to move. And that goes back to our first semester, how we talked about objects in motion stay in motion. So really important thing to note is that velocity is always going to point tangent to the circle. So if our planet is over here, tangent to the circle is going to look like this. If our planet is over here, tangent is going to look like that, all right? So the velocity is always going to be pointed in a different direction. The magnitude of the velocity, though, will always be the same under uniform circular motion. And again, by magnitude, we just mean speed. Let's take a look at our second to last question here, and that has us calculate the period of our planet around the sun. And to do that, we're going to have to go ahead and look at our equations again. So down here, we have circumference equals 2 pi r, and distance equals rate times time. Well, period, if you remember, is the time it takes to complete one cycle. So we're going to need this distance equals rate times time equation. So that just tells us that d equals v times t. And again, t in this equation stands for our period. Well, what does d stand for? D is the distance around that orbit. So d is the total distance of one complete orbit. And in other words, we just mean the circumference. And we know that the circumference, right, in case we forgot, is right here, is equal to 2 pi r. So therefore, we can go ahead and substitute d for circumference. So we get 2 pi r is equal to v times t. And again, we're solving for t, so let's just go ahead and get that by itself while we're at it. T is equal to 2 pi r over v. And this is still the same r that we used before and still the same v from before. It would appear as though we've come full circle, because our circle is our orbit. So the r, or radius of our orbit, is that distance from the center of the orbit, in this case the center of the sun, to the center of our planet. So once we plug in all of our numbers, we find out that our period should be 2.65 e to the 9th seconds. And they want us to show it in multiple ways. So here's seconds. And if I want to convert this into minutes, I'm going to need to divide by 60 here. And I find out that that is 4.42 e to the 7th minutes. And again, if I want to convert this into hours, I'm going to divide by 60 here. And I get 7.37 e to the 5th hours. And lastly, if I want to convert this over to days, I'm going to go ahead and divide by 24 because there's 24 hours in a day. And that is going to give me 3.07 e to the 4th days. And then finally, if we want to take all this and convert it into years, well, in order to find years, we're going to go ahead and divide by 365 because all of this time is relevant to Earth time. And we find out that our planet takes 84 Earth years to complete one orbit. And why is that important? Because it asks us for the last question, based off of these calculations and the picture below, what is the name of our planet? And if we look at this picture here, we can see that it has the time that it takes for each of these planets to orbit the sun. We have 88 days, 255 days, 365 days, 685 days, 12 years, 28 years, 84 years. I just saw that somewhere. Well, bingo. That means that our planet that we picked was Uranus. And we can go ahead and write that down here as our planet, Uranus.